Have you ever wondered how life itself is possible? The answer lies in the fascinating field of organic chemistry. Imagine a world with no life, no plants or animals, no you or me. Pretty grim, isn't it? Now what if I told you that the existence of life as we know it hinges on the intriguing and complex world of organic chemistry? Yes, you heard that right. Organic chemistry is the unsung hero, the silent force that drives life on Earth. Organic chemistry, in the simplest terms, is the study of carbon-based compounds. Now you may be wondering, why carbon? What's so special about this particular element? Well, carbon, my friends, is the element of life. It's the backbone of every living thing on this planet and beyond. It's the element that forms the basis of all known life, from the smallest microorganism to the largest blue whale. But organic chemistry isn't just about carbon. It also includes the study of hydrocarbons and their derivatives. You've probably heard of hydrocarbons before. They're the compounds that make up fuels like gasoline, natural gas, and coal. But did you know that hydrocarbons also play a critical role in life processes? They're found in natural substances like fats and oils and are essential components of our DNA. Now let's talk about the derivatives of hydrocarbons. These are compounds that are formed when one or more hydrogen atoms in a hydrocarbon are replaced by other elements or groups of elements. These derivatives are incredibly diverse and can be found in everything from the food we eat to the medicines we take. So, whether we realize it or not, organic chemistry is all around us. It's in the air we breathe, the food we eat, the medicines we take, and even in the very cells that make up our bodies. Organic chemistry is not just a subject to be studied in science class, but an integral part of our everyday lives. So it's clear that organic chemistry is at the heart of life on Earth. But how exactly does it work? The magic of organic chemistry is largely due to one element, carbon. So what's so special about carbon? Well, it's all about the bonds. Carbon is a master of connection, a social butterfly of the atomic world. It has 4 electrons in its outer shell, which means it can form 4 covalent bonds with other atoms. Covalent bonds are strong, stable, and they form when atoms share electrons. This ability of carbon to form 4 of these robust bonds makes it incredibly versatile. But that's not all. Carbon doesn't just form bonds with other elements, it's also quite fond of bonding with itself. Think of carbon atoms as Lego bricks. Just like how you can stack and arrange Lego bricks in countless ways, carbon atoms can link together to form chains, rings, and more complex structures. This ability to build elaborate molecular structures is the reason why carbon is at the heart of an astounding number of compounds, over 10 million known to science. Here's another interesting thing about carbon. It's not just about the quantity of compounds it can form, but also the quality. Carbon forms the backbone of many stable, complex compounds. It's the foundation of the molecules that make life possible, from DNA to proteins to sugars. Carbon compounds can be solid, liquid, or gaseous, and they can exhibit a wide range of physical and chemical properties. And if that isn't enough magic for you, how about this? Carbon is the only element that can form long chains of atoms, also known as polymers, without breaking apart. This property is what makes plastics, rubber, and many other materials possible. So with carbon, it's not just about the bonds it forms, but the remarkable diversity of structures and compounds these bonds create. It's a testament to the adaptability and versatility of this tiny atom, and it's why carbon is the superstar of organic chemistry. With carbon's unique properties, we can start to understand the complexity and beauty of organic chemistry. Just like any language, organic chemistry has its own alphabet and grammar, the structural formulas. Now, if you're wondering what structural formulas are, think of them as the blueprints of molecules. They depict the arrangement of atoms within a molecule, showing us exactly which atom is connected to which. In other words, they're a chemist's version of a roadmap, illustrating the complex highways of atomic bonds that constitute a molecule. Structural formulas come in various types, each offering different levels of detail about a molecule. At its simplest, we have the molecular formula, which tells us only the types and quantities of atoms present in the molecule. It's like knowing the ingredients of a recipe, but not how they're combined. Then, we have the full structural formula. This is the most detailed version, showing us exactly how the atoms are bonded together. It's like having a detailed recipe, complete with instructions on how to combine the ingredients. But chemistry, much like life, isn't always about the details. Sometimes, we need to see the bigger picture, and that's where condensed and skeletal structural formulas come in. These provide a simplified view of a molecule, allowing us to quickly understand its general structure without getting lost in the details. It's like looking at a simplified map of a city, where you can see the main roads and landmarks without being overwhelmed by every single side street. So why are structural formulas so important in organic chemistry? Well, they guide chemists in predicting the behavior of organic compounds. Just as knowing the layout of a city helps you predict traffic patterns, understanding a molecule's structure can help predict how it will react under different conditions. It's all about knowing the lay of the land, or in this case, the lay of the molecule. In conclusion, structural formulas aren't just a way of representing molecules. They're a fundamental tool in the chemist's arsenal, helping us understand and predict the complex behaviors of organic compounds. Structural formulas provide a map to navigate the complex world of organic chemistry. Now let's turn to the key that unlocks the behavior of organic compounds: functional groups. Imagine a party where everyone is mingling and interacting. Some guests are the life of the party, drawing everyone's attention, while others might prefer to quietly observe. In the world of organic chemistry, functional groups are like these guests. They are the parts of organic molecules that participate in chemical reactions, and their behavior determines how the whole molecule behaves. Think of an organic molecule as a house, and the functional groups as the rooms. Just like the kitchen, living room, and bathroom each have unique functions in a house, functional groups each have their unique roles in an organic molecule. They can make a molecule more reactive, less reactive, or even completely change its behavior. Functional groups are made up of specific arrangements of atoms. They often contain elements like oxygen, nitrogen, or sulfur, which have different electronegativities or tendencies to attract electrons. This variation in electronegativity can create areas of charge within the molecule, which can then interact with other molecules. For example, let's consider the alcohol group, which contains an oxygen bonded to a hydrogen. This group is quite reactive, owing to the polar nature of the oxygen-hydrogen bond. This reactivity makes alcohols good solvents, and they're often found in products like antifreeze and perfumes. On the other hand, the carbonyl group, which consists of a carbon double bonded to an oxygen, gives rise to a whole host of compounds, including ketones and aldehydes. These groups are often involved in fragrance and flavor compounds. So, functional groups, with their unique arrangements of atoms and varying electronegativities, give organic compounds their diverse properties and behaviors. They are the reason why organic chemistry is such a vast and fascinating field, filled with millions of different compounds, each with its own unique characteristics and reactivity. Functional groups are like the personality traits of organic compounds, defining how they interact with the world around them. So now we've explored the basic elements of organic chemistry, let's recap. Organic chemistry is a vast and intricate domain of science that underpins life as we know it. It's an exploration into the very heart of life's processes, a journey into the molecular world where the building blocks of existence are formed, manipulated, and understood. One of the key players in this grand narrative is carbon, the versatile actor capable of forming an array of bonds with other elements. Carbon's unique ability to form long chains and rings allows for the creation of a diverse array of molecules with varying properties. This inherent flexibility is what makes carbon the star of the show in organic chemistry. We then delved into structural formulas, the language of organic chemistry. These diagrams provide a visual representation of the molecule, detailing the arrangement of atoms and the bonds between them. By studying these formulas, we can predict the physical and chemical properties of the compound and understand how they will interact with other molecules. From the structure, we move to the functional groups, the key to understanding organic compounds. These groups of atoms determine the behavior of the molecule, influencing how it reacts with other compounds. They are like the personality traits of a molecule, shaping its interactions with the world around it. In essence, organic chemistry provides us with a set of tools to understand and predict the behavior of molecules. It offers a roadmap to the molecular world, a guide to the intricate dance of atoms and bonds that forms the basis of all life. Remember, organic chemistry is not just about memorizing structures and formulas, it's about understanding the principles that govern the molecular world and applying these principles to predict and explain the behavior of molecules. With these tools in hand, you're ready to delve deeper into the fascinating world of organic chemistry, the chemistry of life itself.